Hello, welcome to the OK Math. Today we are going to explore the concept of surface area and volume of 3D composite figures. Since this concept is not abstract, in fact, it is quite concrete and visual, I hope you have less fears during this lesson. To save your precious time, I'll show you what we're trying to achieve in this lesson from the get-go. There are 3 questions that you should be able to solve by the end of this lesson. Here's the first question. Find the surface area and the volume of this composite figure. If you think you can solve this, please pause the video and try. Feel free to use formula and calculator if that's something that will be given to you in class. Alright, here's the answer to the first question. Excellent job for trying. Now try the next one. Again, find its surface area and the volume using formula and calculator if you need. Alright, here is the answer to the second question. Please keep in mind that these questions are what we're trying to achieve by the end of this lesson. I'm simply giving you a chance to try by yourself before I teach you, in case you already know how to solve them. In that case, you don't really need any extra lesson, but more practice to master the concept. Let's move on to the last question. Pause the video and try this. Don't stop challenging yourself. Here is the answer to the last question. If you'd like to learn how to solve those 3 questions correctly, please continue watching this video. Before we enter the 3D world, let's master 2D world, starting from the very basic shapes. When a shape has 4 sides forming 90 degrees at every corner, it is called rectangle. Square is a special case of rectangle. When all sides of rectangle have the same length, we name this special case square. Next shape is a circle. I would like to explain its property and definition someday in the future lesson. But for now, let's just review some terminologies. For this lesson, you need to know what is diameter and what is radius. Here are different types of triangles. When a triangle has a corner that is 90 degrees, it is called right triangle. If 2 side lengths are equal, simultaneously 2 corners have the same angle measurement, it is called isosceles triangle. If all 3 side lengths as well as all corner angles are the same, it is called the equilateral triangle. Okay, let's talk about the area. For a rectangle, which includes square, you multiply the length with its width. Area of rectangle is length times width. For the area of circle, you must know its radius. If only the diameter is given to you, you can always find the radius by halving the diameter. Area of circle is pi times radius squared. Finding the area of a triangle is also super duper straightforward as long as you can identify its height. Identifying the height of a triangle is the only potentially tricky part. I'm not joking. Check if you can identify the height of an obtuse triangle. Anyway, the area of triangle is a half of base times height. Congrats, students! We are finally done with the elementary 2D world. Yay! In this next 2 slides, we'll briefly review the Pythagorean theorem, our best pal from junior high along with the function. Then, we'll finally enter the 3D world. Pythagorean theorem is a relation among sides of right triangle. In this lesson, we'll use the theorem to find a missing side length. To use the theorem, you must make sure that a given triangle is a right triangle. Then identify the longest side of triangle, which is the one facing the 90 degrees. This side is always called hypotenuse. The other two sides are called adjacent and opposite. In trig lesson, labeling them precisely to the corresponding side is critical. But in this lesson, you don't have to worry about which one is adjacent and opposite, as long as you got the hypotenuse correctly. According to the Pythagorean theorem, the longest side square is equal to the sum of two other side squares. What if a given triangle is not a right triangle? Well, in that case, make it into right triangles. Listen, you can draw a line to split a triangle into two right triangles. Did you break any law? No. Problem solved. Now you got your right triangles. You can identify the hypotenuse of each triangle and use the Pythagorean theorem. Welcome to the 3D world. I would like to introduce to you the basic 3D figures that we'll see again and again in this lesson. Here we got a cube who has perfectly identical 6 square sides. Next is a prism who has a rectangular side. A pyramid, as we know, has a square or rectangle on the base and has a triangular side forming a pointy top. A cylinder, which we can find from the shape of beaker or a can, has identical circular face on the top and the bottom. Next row. A cone is another pointy 3D figure like a pyramid, except it has a circular base. A regular tetrahedron, as the name implies, is formed by identical 4 triangular faces. The last two are sphere and the hemisphere, which means a half of sphere. Now it is time to solve 3D figures. By the way, I have a feeling that most of you have a handy formula sheet next to you. Well, here's the thing. How many of you got wrong answer to a very simple question in the past because formulas seem so confusing and gibberish? They even look so similar to each other. I need you to watch the next following slides and understand where that gibberish is coming from. Soon it will become your language. Do you remember how to figure out the area of a square? Yes, it is length times width. Cube is nothing more than 6 squared faces. To find the surface area of a cube, we find the area of a square and times 6. Surface area of a cube is 6 times length times width. Prism is quite similar to the cube, except it has 3 pairs of rectangles. Find the area of 3 different sized rectangles, add them together, and double them. I hope my illustration helps you to understand it better. Pyramid can have either a squared base or a rectangular base. For the squared base one, we have the square for the base and 4 identical triangles for the side. So the surface area of a squared base pyramid is 4 times the area of triangle plus an area of a square. A rectangular base pyramid will have a rectangle for the base, surprise, and 2 pairs of triangular sides. For the surface area of rectangular base pyramid, first you find the area of 2 different sized triangles, double them up to make it as a pair, and add the area of a rectangle for its base. If you're into crafting or origami, the formula for a cylinder surface area will make so much more sense. When you cut open a cylinder and flat it out, you will see its nap having 2 identical circles for the top and the bottom, and a rectangle for the side. The key point here is that the length of rectangle is the same as the circumference. If this is confusing, I highly suggest you to make a 3D cylinder model from its 2D net. Here is the 2D net for a cone. You will see it has a circle for the base and not quite a full circle nor a triangle shape for its side. If you look at the formula, we have pi r squared for the circular base and pi r s for the side. To be honest, it'll be too complicated and time consuming to explain where does the pi or s is coming from at this point. So I'm going to just ask you to understand what does s represent for now. S represents slant height. In 3D cone model, it will be the distance along the slanted side from the top vertex to the circumference, not a vertical height through the model. Here we have a regular tetrahedron. Do you remember what this regular tetrahedron means? Regular in geometry means equal measurement for all angles and for all side lengths. Tetra means 4 in Greek. Hedron means plane faces in 3D figures. So take a look at the regular tetrahedron. Its surface area is simply the sum of 4 triangle areas. Last but not least, sphere's surface area is 4 pi r squared, and hemisphere's surface area is a half of sphere's surface area plus pi r squared for its circular base. Here is good news for you. Volume of 3D figures are surprisingly easy to understand and to solve for. For example, take a look at this prism. What shape do you see on its base? A rectangle, which is length times width. Is the shape consistent from the bottom to the top? Yes. So you can think of prism as a pile of rectangles for each amount of height, like a pile of sheets of paper. Mathematically, we can represent its volume as length times width times height. Pyramid also has a rectangular base, but the shape is not consistent throughout the figure. It gets smaller and smaller as we move up. Therefore, the volume of a pyramid is always smaller than a prism with the same base and height. In fact, it turns out to be 1/3 of a prism that shares the same dimensions. Like a prism, cylinder has a consistent shape throughout the figure from the bottom to the top, except it has a circular base instead of a rectangular base. Therefore, the formula for its volume is pi r squared times height. Cone is like a pyramid, except it has a circular base. The figure gets smaller and smaller as we move to the top. So, as you can assume, it will be 1/3 of a cylinder. Sphere's volume formula is tricky to understand at this point, but really easy to recognize. It has pi, which indicates a relation to circle, and it has r cubed, which implies that it's for a 3D figure. The formula for sphere's volume is 4/3 times pi r cubed. Hemisphere is simply a half of sphere's volume. Don't worry, students. We'll not find the volume of a triangular prism, neither a regular tetrahedron at this point. It can be a bit confusing. Based on the previous examples, finding the volume of a triangular prism shouldn't be too complicated, but I don't think it's necessary, so let's move on. Composite 3D figures that we need to deal with in this lesson, they're nothing more than a combination of tweaked basic 3D figures. Are you ready to explore? Here is our first example of 3D composite figure. We got its front view and the top view. Based on the pictures, imagine the 3D figure it's describing. You got this? Now, here's the question. What 2D shape do you see on the figure? How many of those shapes are there? Is this what you're thinking? Excellent! To find this 3D figure surface area, all we need to do is adding up the areas of these 8 triangles. And we for sure know how to figure out a triangle area. It is base times height divided by 2. Now, let's figure out its volume. This composite figure is made of few basic 3D figures that we studied in the previous slides. Do you see any prism, pyramid, cone? What basic figures do you see? I see this composite figure as a combination of 2 square base pyramids, one on the top and one on the bottom upside down. So the volume of this composite figure will be addition of 2 pyramids' volumes. And yes, we do know how to figure out the volume of pyramid. Students, it is time to fire some of your neurons. Here, give it a try before we move on to the next example. Find the surface area of the following composite figure. Here's my approach to the question. From the previous slide, I remembered that the surface area of this 3D figure is the same as the sum of areas of 8 triangles. So I need to use the formula for an area of triangle, which is base times height divided by 2. In the picture, the base of triangle is given to us, that is 10 centimeter. Height of triangle, however, is unknown. When there's a missing side length on a triangle, I know only one way to figure it out at this point, which is Pythagorean theorem. Pythagorean theorem works only on a right triangle. So I need to cut this equilateral triangle into half, which gives me 2 identical right triangles. The base of the right triangle will be 5 centimeter. The hypotenuse will be 10 centimeter, and I'll call the unknown height as h. According to the Pythagorean theorem, the longest side square is equal to the addition of 2 other side squares. Now to solve for h, rewrite 10 squared as 100 and 5 squared as 25. To isolate h by itself minus 25 from the both sides equal sign, that leaves us with 75 is equal to h squared. Then take a square root on both sides to undo the square on h. H is square root of 75. Once we know the original triangle's base and height, we can figure out the surface area of 3D figure by using the formula A times base times height divided by 2. The final answer is 346 centimeters squared. Here is our next example 3D figure. In order to figure out its surface area and the volume, let's break it down into basic 3D figures that we are already familiar with. I can see this composite figure as a combination of 2 hemispheres and a cylinder. Do you agree? When we say surface area, we're talking about the areas that we can actually touch if the 3D figure was in front of us. The circular bases of the hemispheres and of cylinder will be perfectly attached to each other to form this 3D composite figure. Therefore, we shouldn't count those circular bases as a part of surface area in this case. The volume of this composite figure is very simple to figure out. We add the volume of 2 hemispheres, which is equal to a sphere, with the volume of a cylinder. Okay. I need you to pause the video now and try to figure out the volume of this 3D composite figure by yourself. Let's go! Here is my approach. I recognize this composite figure is a combination of 2 hemispheres and a cylinder. 2 hemispheres are equal to 1 full sphere. Its volume formula is 4/3 pi r cubed. With the given radius 4, I got the volume of sphere to be about 268.08. The cylinder has a radius being 4. Its height can be found by the total height 20 minus height of 2 hemispheres. The height of cylinder is 12. Using the formula pi r squared times height, I got the volume of cylinder to be about 603.19. Composite 3D figure's volume will be the addition of these 2 volumes, which is approximately 871 cube units. What about this composite figure? How would you approach to figure out its surface area and the volume? Yes, break it down into basic 3D figures. Can you identify those basic 3D figures? I'm sorry if that was too obvious. This composite figure is a combination of a hemisphere, a cylinder, and a prism. When you figure out the surface area of this composite figure, please be careful about the overlapping areas. Just like the previous example, we should exclude those overlapping areas from the calculation of the surface area. To help you understand, I have indicated the overlapping areas on the picture using yellow X signs. Remember, surface area means the area we can touch. Thankfully, figuring out the volume is easy peasy in this case. Find the volume of the basic 3D figures, a hemisphere, a cylinder, and a prism. Then add them together. It is as simple as that. Thank you so much, students, for watching this far. Now you have the foundation to solve challenging 3D composite figure questions. Did I say challenging? That's not true. I'm afraid the following question might be too easy to you now. Let's see. Question number 1. Pause the video and solve. Here is the solution to the first question. It is crucial to exclude all the overlapping areas from the calculation when you're solving for the surface area of a composite 3D figure. If you got different final answer, please pause the video and compare the solutions step by step. Next is the volume of the 3D figure. It is quite straightforward. Here is the second question. Pause the video again and give it a try. Was it hard to figure out the surface area? For this question, you need to subtract the partial area from its bases and count the inner cylinder's side areas. I know it does sound confusing. If you need a 3D model to see and touch to understand its surface area, go grab a roll of toilet paper or a paper towel. Then read through the solutions slowly along with the pictures. I promise you that this is not beyond your league. You got this. The volume of this composite figure is simply the outer cylinder minus the inner cylinder. Simple. Here is the last question of today's lesson. Let's do this. The trick of this question is the unit. If a question has measurements with different units, such as millimeter, centimeter, meter, inch, you need to first convert them into one same unit and then solve. Don't mix up that order. Convert, then solve. For this question, I have converted millimeter to centimeter and solved in the green box. Also, I have converted centimeter to millimeter and solved in the rosy colored box. To figure out the volume, I converted millimeter to centimeter first and used the Pythagorean theorem to find the height of the cone. Once I got the height, square root of 96, I substituted it into the formula and found the cone's volume, approximately 41 centimeter cubed. This slide shows the exact same procedure, except in this case I converted centimeter to millimeter. Either answer will be correct since I did not specify what unit the final answer needs to be. In this short video, we reviewed basic 2D shapes and basic 3D figures. Then, we covered how to figure out surface area and the volume of 3D composite figure. I hope this video helped you understanding the concept even a bit. Anyway, thank you so much for watching. Until we math again. Bye!